Hey guys, welcome to All Electronics. I'm Gregory, and in this video we are going to see how we can model the PLL charge pump using LTSpice. So we are going to understand how the charge pump works in our project here in the 10 GHz source project. You can take a look on the project clicking here on the balloon, and we are going to go to LTSpice to simulate it, to understand the behavior and to decide what values of capacitors and resistors we are going to use on the loop filter. Okay, first things first, guys, we need to understand how we are going to model the small signal behavior of the charge pump in LTSpice. Okay, what happens here in our project is that we don't have a charge pump with current sources. Okay, so when we are dealing with high-end PLLs, integrated circuits, we have a true current source in the phase and frequency detector, as I explained it in the last video about the PLL loop filter. Okay, and here I emulated the effect of the current source using this structure here. So we have the common phase and frequency detector using the flip-flops here. Okay, and the AND gate for the reset, and we can emulate the effect of the charge pump for a small signal for the small signal perspective using this diode arrangement here. Okay, and a high value resistor, and this works pretty well in this situation here. So the diodes are used to switch on and off the current direction. So when the reference oscillator is leading, okay, is generating more faster pulses here on the clock of the upper flip-flop, this diode here will be turned on, okay, and we are going to apply 5 volts here on the resistor. Yeah, when the VCO is leading, okay, so when we need to take the frequency of the VCO and get it down, when the VCO is generating faster pulses here in the clock, we are going to put a 0 here in the key Q0, okay, in the negative output of the flip-flop, the inverted output, and we are going to place a 0 here, a 0 volts here in the resistor, because now this bottom diode here will conduct. Okay, and in this node here we are going to have 5 volts or 0 or high impedance. When the two inputs are synchronized, we are going to have high impedance here because neither of the diodes will be conducting. Okay, but here we have, in this node here, we have a voltage signal. Okay, the diodes in conjunction with the flip-flops are acting as a voltage source. And we can transform this voltage source in a current source using a high value resistor. And this is what I made here. I placed a 47K resistor here. Why a 47K resistor, guys? Let's linearize the circuit for the small signal perspective using the DC condition of the circuit. We know that the VCO will be close to the output frequency when we have 2.5 volts in its input. In the control input of the VCO, we need to have 2.5 volts to have it in the correct output frequency, near the correct output frequency. I explained this in the video when I was tuning the VCO. So I tuned the microstrip bandpass filter of the VCO to have this condition. So we know, I'm recording. We know that the condition is an average voltage, a DC voltage of 2.5 volts here over the VCO, okay, in the output of the loop filter. So if we switch here 5 volts, let's draw over this circuit diagram here. If the reference oscillator is leading, okay, we are going to turn on this the upper diode here, okay, with 5 volts, plus 5 volts. We're going to have plus 5 volts here. and I'm ignoring here the voltage drop of the diode. Okay, you can consider the voltage drop of the diode. Here we are not considering because it actually will not matter so much. Okay, so we have 5 volts here. If we have 5 volts here, okay, and 2.5 average DC potential in the other side of the resistor, we are going to have a positive current in this direction of 50 microamps. Is the voltage difference 2.5 volts over 47K. Okay, if, let's undo here, if we're going to if the VCO is leading here and this output here is going down, so we're going to have 0 volts here. Okay, this diode is placing 0 volts here, and now we again have 2.5 volts of difference over the resistor. Okay, but now the current will be in the negative direction. 50 microamps in the negative direction, in the other direction. Current will be sunk from the filter to the diode. So the small signal gain of this charge pump here is 50 microamps. Okay, small signal, guys. When the VCO is very far from the correct frequency, we are entering large signal. The circuit will work okay, no problem. But this analysis here is for the phase domain, only for small signals. So this is correct. We have a current source. We have a current signal from the small signal perspective. We have 50 microamps being sourced or sunk from the filter with this configuration. Okay. Now that we understand this, we can go to the LTSpice to see how we are going to model it. Okay, so here I have the model, but we are going to construct the model. Okay, we can see here the model. We're going to construct the open loop model, and we're going to close the loop to see the results. And here I can spoil you. We have here the open loop filter response, and here we can see the closed loop response. Very nice, and we can see both responses here. Okay, you can see that when the open loop here, the blue response, crosses 0 dB unit gain, we are going to have here, very near to unit gain, we are going to have the 3 dB point knee of the closed loop response. Pretty nice, guys. And this is pretty nice. This simulation here is pretty nice because look what we can do here. We can add also here the behavior of the VCO. So in the VCO, I have a filter on the VCO control line to filter the signal, to have a very clean signal entering the varactor. And we can emulate it here, placing here the schematics of the VCO. And here I placed a 10 picofarad capacitor to emulate the varactor plus the microstrip characteristics. And here we can see the closed loop behavior of the closed loop system with the behavior, the correct behavior of the VCO. This is pretty nice. And you can see here, guys, that the closed loop, ideal closed loop, small signal closed loop is this behavior here. A pretty common behavior in a control analysis of a system. And here we have the VCO, the more correct VCO PLL response, taking in consideration the behavior of the VCO. Pretty nice. So let's start a new project here and let's start doing this, guys. First things first, we are going to place here a source, okay, voltage source to excite the circuits, okay. This will be an AC sort of amplitude unity. Okay, we place the value here because we are going to do a small signal AC analysis. Okay, to have the bode plot on LTSpice. Okay, guys. First thing we are going to do is place here the phase comparator, the phase and frequency detector. And we know that the phase and frequency detector has a gain of 50 microamps. Okay, guys, so it's very simple. We need to find here the voltage dependent voltage source. Okay, and you're going to place here the voltage dependent voltage source, and we are going to start. Oh, guys, we are going to start with the open loop response. Okay, so for the open loop response, we are going to open the loop and not close the loop. So this is pretty nice of using this voltage dependent voltage source here, because we can close the loop very easy, only taking the output of the VCO and feeding it back here on the phase and frequency detector. Pretty nice. The gain of this voltage dependent voltage source is 50 micro. Okay, nice. Now, guys, we are going to start with a simple filter. Okay, we are going to start only with the capacitor to see the behavior as we construct the loop filter. Okay, so let's place here. Oh, sorry guys, it's a current source here. Sorry guys, it's a controlled current source. Sorry, guys, it's a controlled current source, because we are doing the small signal analysis using the current source. So we are going to ignore the resistor. This is important. Okay, this is the small signal behavior of all this circuit here, considering the resistor. Okay, so we are ignoring the resistor. This is important because we are already on small signal behavior using the current source here. Right? Now, guys, now we can place the loop filter here. That will be only a capacitor. Right? Sorry for this mistake, guys. And here we are going to place the VCO. Okay, the VCO is actually the voltage controlled voltage source, E here. Okay, and here is pretty nice because here we can place the VCO, and here on the VCO, guys, we're going to generate a signal here. Okay, let's call the signal VCO, right? And here on the VCO, we can place a Laplace function, transfer function. This is pretty nice from LTSpice. We can place here Laplace, using uppercase L here, Laplace equals the gain of the VCO, 25 meg, over S. Remember that the transfer function of the VCO is an integrator. I explained it on the last video. Please take a look on the video clicking here up in the balloon. So we have the integration action with the gain. Okay, 20 here actually. 20 meg. Okay. Now we have the signal for the VCO. We are going to place here a capacitor. Let's place here 22 nano. I think is okay for this. So you can see the first result here. We are still recording. Yeah, recording. And we are going to place here an AC analysis. Decades, number of points 1K. Start frequency, let's start from 10 Hertz going to 100 meg. And we have it, and we have here the simulation. We're going to close my other simulations, and now we can see it. Is it right? Is it right? Now we can see, guys, the open loop response of the system. Easy, guys. So take a look here. Let's take a loop here. I'll put it here so it's okay on the video. Pretty nice, pretty nice. We can see that we have, now we are in game. We can see that we have a very high gain at DC. Because why we have a very high gain at DC? Because we have an integrator here. Two integrators in this small signal analysis here. The integrator of the phase comparator and the integrator of the VCO. The actual circuit in real life doesn't have this perfect integrator here. The charge pump of our circuit is not a perfect integrator. Okay, but for small signals, it is, as we understand it here. Okay, and we can see here that the phase, we have a pretty high gain. We have it crossing here unit gain at around 33 kilohertz. We can see it clicking here, and we have this small window here where we can see that it gonna crosses here at 33 kilohertz. Pretty nice, yeah. It gonna cross in, and the phase is 108 degrees, as we predicted. Okay, the phase is 108 degrees, as we predicted. And we know that when we close the loop with unity gain, crossing unity gain with 108 degrees of phase, we are going to have an unstable loop. This loop here will not work. And we can make it here, we can test it here, closing the loop, guys. We can open here and close the loop. We can place here a label, okay? So now we connected the output of the VCO and closed the loop. But I will here, for this drawing here, I will connect it with a wire because it's for the video is easier to see that now the loop is closed. And do you agree with me? Now that we actually closed the loop here, we can see that the loop is closed. So now the phase comparator, phase and frequency detector, is actually measuring the output of the VCO, closing the loop. And now we're going to see that the system is unstable. Let's simulate it. And take a look at this, guys. This is pretty beautiful, guys. We see the instability of the loop here. Actually, here we have a much larger peak here. This peak here is actually infinity. But we are not seeing it here because we have discrete steps in frequency. Okay, we have 1,001K points per decade here in the simulation. If we increase it here, we can try to increase it to 10K points per decade. We are going to see that the peak will be higher. Yeah, now the peak is higher here. Because now we are sampling closer to the infinity. Exactly closer to the infinite point. Okay, but we know that the system is unstable, so we can use 1K points here to see that the system is unstable. And now we're going to correct it, placing one more resistor, adding a 0 to the transfer function. So let's open here the loop again. Let's open the loop here. Now we're simulating open loop response. Let's see the open loop response here. Nice. And now, guys, we're going to take this capacitor here and place a series resistor here. What's gonna happen, guys? This series resistor here will create a lead compensator. We're going to advance the phase a little, and we're going to control the point where the phase is advanced to create phase margin in the system. So we are approaching this final loop filter here in steps, understanding what's really happening in the circuit. Yeah. So let's see here. Let's place here, guys, 10 ohms. Okay. And let's see the difference here. We are going to see the difference mainly on the phase. Take a look at what's gonna happen to the phase of the open loop response. Look at these guys. Look at these guys. We have lead compensation. We are adding phase in the system. And it's clearly to see it here, guys. Very clear to see it here, that when we approach this point here of the zero in the transfer function, we see that the phase starts to lead. Take a look on the phase, guys. The phase here is returning to 9 degrees. We are not adding phase, we are subtracting phase. And this will stabilize the loop if we do it properly. So here we can see that we are crossing 0 dB. Let's see where we are going to cross 0 dB here. We have negative 177 degrees of phase. We have 3 degrees of phase margin already in the system. The system is pretty unstable, but it is theoretically stable. The system now is theoretically stable because we have phase margin. Very low, a small margin, but we have phase margin. And if we close the loop now, we are going to see that now the peak is lower. And now it's not an infinite peak. This system here will not go to infinity because we have phase margin, pretty low phase margin, but we have it. This is pretty interesting. This is beautiful to see it working here on LTSpice, guys. So what we're going to make now, guys? First thing we are going to make is that I want to open a bit the loop here, the loop bandwidth, okay? So we saw that the 3 dB point of the closed loop filter response of the PLL will be very near, almost coincident with where we cross 0 dB in the open loop. So I want to cross 0 dB closer here to 100K. So probably we can place here 47 capacitor. Now we are crossing, oh yeah, almost spot on. Yeah, it's nice. Now we are crossing here in 75 kilohertz. So we have a broader bandwidth PLL now. Okay. Now we are going to place the resistor to control the phase margin. And let's place here a resistor of 100 ohms. Pretty nice. Now we can see that we are crossing 0 dB here with negative 168, 22 dBs here. No, sorry, 12 dBs of phase margin. We need more phase margin to be stable. We need at least 50 degrees of phase margin. So let's increase it here. 390. Pretty nice. Now you see that we are also changing here the crossing point a bit. So this is a complex system that you need to change the values of the capacitors and resistors to make it work. We changed a bit the crossing point to 85 kilohertz. Is not a problem here. I actually want a broader PLL loop. And now we have, let me think, 45 degrees of phase margin. Yeah, here you can see negative 134, 35 here. So now we have a pretty stable loop, guys. Man, this is so beautiful. Let's close the loop and see. Beautiful. This is beautiful. We have a closed loop, stable closed loop now, guys. And we measure all these values here are measured. Are measurements from the VCO. I measure this value, these 50 microamps here. We engineer it and it's working. It's working beautifully. Remember, guys, here in our project here, we have a sampler, and this sampler is not a divider. This is important. If you have a prescaler, the prescaler is a frequency divider, and the prescaler will look like a divider here. Okay, so we would have an attenuation in the closing path of the PLL. So if here our PLL, guys, is connected in this way here. Okay, let's place it here. This is important. It's important to mention it. The PLL of our design is connected in this manner here, because we are using a sampler, and the sampler down converts, it shifts the VCO output to the correct frequency for comparison in the phase and frequency detector. Okay, if you have a prescaler, we are going to have here a divider, yeah, that's dividing the phase. Okay, so let's say you have a 128 divider, so the divider gain here in the phase domain is 1 over 128, okay, for a PLL with n equals. So if you have a prescaler, you need to place this attenuation here in the closing path of the PLL. And this is why now we're going to understand why I chosen a very low current here, guys. Are you seeing why we use it a very low current here? Because if we have this attenuation here, we have a much smaller open loop gain, guys. You can see that the open loop gain for our design using the sampler, oops, sorry. You can see that the open loop gain here, guys, is 160 dB, is pretty large. So I designed a pretty low gain charge pump here to attenuate a little this pretty high gain. Okay, so we start with a lower gain. If we use a common current here, let's say here 1 milliamp, it's a common current for the phase and frequency detector. Now we have 108 dBs, guys. We are crossing much in a much higher frequency. Let's see, take a look at where we are going to cross here. 800 kilohertz. 800 kilohertz. Pretty difficult to make this PLL stable with a very high gain current source. If you have the attenuation, the prescaler, we are going to attenuate it here. The attenuation on the open loop would be here. So it would decrease a little this gain. But as we don't have, we have the sampler, we need to have an engineered pretty low gain here. So I chosen 50 microamps. Now we are crossing in a reasonable frequency here. Okay, guys, we are approaching, we have the system is stable here with very good phase margin, and this video is taking so long, 30 minutes, and pretty good phase margin. System is stable, it's gonna work. Okay, and the bandwidth is close to what we want. Let's see where we have the 3 dB bandwidth. 3 dB bandwidth here is pretty close to 100K, where I want. Pretty close to 100K. Perfect. And now, guys, we can increase a little the performance of the phase looped filter, phase locked loop, sorry. We can increase a little the performance, adding one more capacitor. This capacitor here. After we crosses 0 dB, so after we cross 0 dB here, guys, we can add a pole pole again here, somewhat here, to stiffen the curve again, closing more the loop. Okay, making the loop filter with a higher slope, a 40 dB slope. Now we have a 20 dB slope on the closed loop response, and we can have a 40 dB slope in the closed loop response, adding a capacitor here. Pretty easy. Easy. So let's engineer this capacitor to be let's see here, guys. I am more a practical guy, so I start to test values here to see what's happening. If you understand a little bit more of control theory, you can calculate the pole position, the zero position, and all of this. Here I'm showing for you a more practical way of doing the design. Okay, so let's place here 407 pico. 407 pico, guys. The pole is somewhat here. Yeah, we are crossing here in the same frequency. We still have a pretty good phase margin, but now you can see that we have this 20 dB slope here, and here we come back to a 40 dB slope. So now the closed loop performance will have 40 dB slope after the 3 dB point. Take a look here, guys. Now we have a much stiffer closed loop performance here. So now we are filtering more noise from the reference. As this is a PLL, now we have a stiffer angle of attack in the bandwidth of the filter. Now we are filtering more the noise, the higher frequency noise of the reference in the PLL. So the shape of the filter here, you are going to choose to model the phase noise. Okay, and in this situation here, I have a pretty clean phase noise reference because I have a crystal reference. So I'm trying to have a broadband bandwidth in the PLL to control the VCO over a broadband bandwidth to have a cleaner VCO. Okay, and you can see that this control here, this peak here, guys, is what generates the phase noise performance, the phase noise characteristic of a PLL. You can see in the output of the PLL, you can see in the last video I posted, the circuit working. You can see clearly the response of the PLL doing a shape with a bump. The bump is this peak here in the closed loop response, guys. Because actually this response here will shape the phase noise and the relation of phase noise from the VCO and from the reference. Yeah? So guys, I hope you enjoyed this video. I think it was very clear here to see how to emulate it. And now you can you can copy to see the open loop and the closed loop at the same time. You can copy the circuit. Yeah? You can copy the circuit. You can have here VCO2. Okay, you can run this one in open loop, in closed loop. Oh, sorry, you need to also copy this. Yeah, these are going to run in open loop. So now we have open loop and closed loop here. Let's see if it can work. We have open loop and closed loop here. Nice, beautiful. This is pretty beautiful, guys. Thank you for watching. I hope you liked this video. If so, please subscribe to the channel, send to your friends, send in the groups, post it in Twitter. Help me reach 3K subscribers. Okay, guys. Thank you so much, and I see you in the next video of All Electronics. Bye.